All the planets in our solar system evolved out of the same flat disk of dust and gas 4.5 billion years ago. Astronomers see similar disks around young, distant stars, but even with our most powerful telescopes, we can't see planets forming. They're too far away. But Saturn's rings are right on our doorstep, a veritable snapshot of a mini solar system caught in the process of formation.
Looking at the rings, we're looking at the formation of planets or bodies in an arrested state of development. It's like you took the beginning stages of the formation of the planets, but stopped it.
Cassini shows structures forming spontaneously inside the rings.
They don't even need to be tickled. They don't need to be disturbed into forming structures. They form them on their own.
Does this tiny moon, captured in the process of formation, show us how the Earth started its life?
You get something that just happens to form out of random processes, and that mimics what astronomers think they're seeing in protoplanetary disks surrounding other stars in the cosmos around us.
Cassini sees curious propeller-like structures inside Saturn's broad A-ring. They're caused by ring particles washing over tiny hidden moons. The particles collide with the moons, sending them into random, ever-changing orbits, sometimes closer to Saturn and sometimes farther away. Perhaps similar forces influence the Earth's formation around the Sun, pushing it into closer or wider orbits. Saturn's rings also help us understand why planets stop growing. A walnut-shaped moon called Pan sits near the middle of Saturn's A-ring. Pan should be huge with so much ice around to gobble up, but it's tiny, only 20 miles in diameter.
If you have a moon embedded in a disk of ring particles, you might naively think it just accretes ring particles until it grows into a bigger moon. But actually, we find moons create gaps in the ring around them. So Pan has created the Encke gap, Daphnis has created the Keeler gap.
Rather than pulling ring material in, Pan appears to push it away. As the moon passes the slower-moving material outside it, Pan's gravity slings the particles into wider orbits. The faster material inside Pan's orbit is slowed as it passes the little moon, causing it to fall away towards Saturn. This may explain why multiple planets form around stars, instead of single giant planets that eat the whole buffet. For most of history, the only moon we've been able to study up close is our own. Multiple deep craters tell a powerful story. The moon is dead. There's no active geology or weather to wipe away these ancient scars. But what about the moons around other planets, like Saturn? Are they dead too?
Our first assumption about Saturn was that the moons would be like that. Cold, dead, lifeless, relics from the early solar system.
It wasn't until we invented spacecraft that could go to these moons that we discovered how incredibly diverse our solar system truly is.
At first glance, Saturn's moons bear striking similarities to our own. Rhea and Ione display their cosmic battle scars with pride. But here the craters are made from water ice, not rock. Mimas bears a dramatic reminder of a colossal collision.
There's one tiny moon called Mimas, which has a huge crater on it, and it looks so much like the Death Star from Star Wars that when people first saw images of Mimas, they thought it was a joke, that we put a little image of the Death Star in there just for fun. But no, that really is what it looks like.
Other moons are marked by Saturn itself, like Iapetus, the moon with two faces.
Now, Iapetus is an icy cold moon, but one hemisphere is dark and dusty, and the other one is absolutely pristine, clear ice.
This split personality initially baffled scientists. Then Cassini turned its magnetic detectors to this tiny moon.
We now know it has to do with the way dust interacts with the magnetic field of Saturn, coating one side of the moon as it goes around.
Some of Saturn's moons are marked by active processes from within. Take Enceladus, an icy moon barely 300 miles across. Nobody paid it any attention a decade ago. Today, it's a geological rock star. And this is why. Enceladus orbits inside Saturn's outermost ring, the E-ring. The E-ring puzzled scientists because they couldn't figure out how a ring so broad and so diffuse could hold itself together. The Cassini team decided to take a close flyby of Enceladus to solve the mystery.
Did it have something to do with keeping the particles together? What was the connection between the E-ring and Enceladus? Well, now we know that Enceladus is actually responsible for the E-ring being there in the first place.
2005, Cassini captures an astonishing sight. 100 geysers shooting ice particles miles into space from cracks in the South Pole. Enceladus is hurling its guts into space at a colossal rate. As Enceladus orbits Saturn, these icy plumes feed a vast, shimmering halo around the planet, the mysterious E-ring. This icy plume also interacts with Saturn's magnetic field, creating a plasma cloud of charged particles. The particles race along Saturn's magnetic field lines and slam into Saturn's polar atmosphere, raising huge ultraviolet auroras. Geysers explain the E-ring, but how can they exist on a frozen moon a billion miles from the sun? On Earth, geysers form in highly volcanic places where water comes into contact with hot rocks. Enceladus, so small and so far from the sun, should be cold and dead. What heats it is Saturn's gravity.
The source of the heating on Enceladus is the eccentric orbit of that moon. Sometimes it's a little closer to Saturn, sometimes it's a little further away. And that heating on Enceladus from that kneading, gravitationally making the moon stretch and pull, is what warms the interior, causing the activity on Enceladus that we see today.
The gravitational pull of Saturn reaches deep into Enceladus, beyond its water ice exterior, gripping its rocky core. As Saturn's grasp strengthens and weakens, it massages this cold, rocky heart, bringing it to geological life with frictional heat. The heat melts the ice around it, creating a vast subsurface lake. This water jets out through huge cracks in the surface ice. On Earth, where there's liquid water, there's life. Could Enceladus have what it takes for simple organisms to exist?
Once Cassini saw these geysers, the scientists knew they had found something extremely wonderful. They actually changed the mission of Cassini itself, changed its trajectory.
We sent the Cassini spacecraft to fly very, very close over these cracks where the water was rushing out.
Scientists clung to the faint hope that the water would contain salts and organic molecules like ammonia, the building blocks of life here on Earth. Stunningly, Cassini sensors tasted them all in abundance.
In that plume, there's organic material. It's not water, it's a soup. That's incredible. All the main requirements for habitability: energy source, liquid water, a source of biological nitrogen and ammonia, organic material, and the samples are coming up into space. There's a big sign, free samples, take one.
There could be life that could have evolved there. Now, we don't know, we haven't seen it, but the conditions there are as good there now as they were on Earth 3 billion years ago when life arose here.
The sensational realization that Enceladus may harbor life has sparked intense debate about future missions to find it. But it has a rival for those precious research dollars, because Saturn's largest moon, Titan, could also be home to life, bizarre life, and we may have already found it.